Let's begin with this example of ZTransform. The sequence given to us is the following. Xn equals to an un, the unit step. Let's now plot for an. I'm plotting for, well, if I want to put, it will be n, and this is a0 for, and then a0 of course is 1, and there's nothing in between because this is a discrete sequence. So this is a1, and the second one is a2 at time index 2, and so on and so forth. This is a geometric sequence. From our previous studies, we know how to convert a geometric sequence into a geometric series, and we plug in the xn into this expression, and we take the ZTransform using this equation over here. And we know that this is a geometric series, and there's a closed form solution for this guy, which is this equation on the top, provided that this term is less than 1. We would explore how to do this as a revision in the next few slides, but take note, there is a closed form solution for the series. Although it is an infinite series, because this is an infinite number of terms, in particular because of u of n, we only start from the index k equals to 0 to k equals to infinity. Now, provided that this term is less than 1, then you'll realize that if this term is less than 1, as k goes up to infinity, this term will become smaller and smaller very quickly, and hence the sum converges. However, if this term over here is not less than 1, for example, is equals to 2, then you'll realize very quickly that as k goes bigger and bigger, then the term become larger and larger, and the sum doesn't exist anymore because we are trying to sum across infinite k terms of them. So that is why the second line here says that it's undefined if this particular term is greater than or equals to 1. Okay, now, so in the table given to you, on the left is the time, or I should say the discrete time representation. And on the right here is the ZTransform representation. And of course, we have to say that the ROC in this particular case is alpha z minus 1 is less than 1. So you have 3 columns here: the time representation, the ZTransform representation, as well as the region of convergence. Let's continue to study the ZTransform representation. You multiply by z and multiply by z, so that we are going to remove the negative powers of z. So on top will become z, in the bottom will become z minus alpha. So these two representations are identical. One is in negative power of z, and one is in positive power of z. Depending on which one you like to deal with, you can choose either one. However, if you are asked to plot the pole and zero diagram, let's see what happens. Well, this is h of z. Let us now substitute when z is equals to alpha. When z is equals to alpha, the denominator becomes 0. And z, which is alpha divided by 0, becomes infinity. So at this point here, we are going to draw actually a cross to say that there is a pole position here. What about z equals to 0? Actually, we should draw a little circle here to say that at z equals to 0, there is a 0. So this is the region of convergence diagram. We'll also again give more details later on. This is just an overview. Alright, let's do the geometric series exercise. Let's recap. We are given the sequence, and the sequence is a to the power of n, and n is an integer. Not only that, it is only a causal sequence, so I'm going to draw first a un, which is the causal sequence, and I will use this little arrow here to say that from this value onwards is time n equals to 0, n equals to 1, n equals to 2, and so on. But before that, the values are all zeros. So this is the anti-causal part, and on the right hand side after the arrow is the causal part. Now let's plug the equation in. I begin for a bilateral Z-transform. However, because of the un, then the starting index becomes n equals to 0, because when n equals to -1, -2, the values are all 0 anyway, so we can now change the index. When we have these little equations here, we will collect the power of n to be outside, and we reach this equation here. So now when we recognize this is a geometric series. We are summing up a sequence of terms that behaves like this. So how do we reduce it into a closed form solution? Is this: we let s of n be the sum of, from k equals to 0 to n terms, the first n plus 1 term. So if we let r equals to this term here, then it will be r0 plus r1 plus r2 until rn. Now the trick to solve this geometric series is to first multiply Sn by r. So what happened is that all the terms now has the r increased by a power of 1. So it's r1 plus r2, so on and so forth, until the last term is rn plus 1. We now apply the trick. The trick is this, which is Sn minus Rsn, which will give us this equation, R0 minus Rn plus 1. Now, let's see what we do. Sn, which is this term over here, minus Rsn. We get R0 minus this whole term. Well, since there's no R0, we get R0. But R1 is minus with R1. R2 is minus with R2. Rn is minus with r to the power n here, leaving with us minus Rn plus 1. So this is how we get this equation here. We now can collect the Sn outside, and we have 1 minus r to the power n plus 1, because r to the power 0 is this guy. Now we can shift this term into the denominator on the right hand side, giving us this equation here. Now what is interesting now is this: we are still left with this term, but if this term absolute value is less than 1, as n tends to infinity, absolute value of r will tend to 0. However, if absolute value of r is greater than 1, then r to the power of n tends to infinity as n tends to infinity. So we are hoping that the absolute value of r is less than 1. Now, so we just state this point. We say that if the absolute value of r, which is this little term here, a to times z minus 1 is less than 1, then this term becomes 0. And therefore, we have s equals to 1 over 1 minus r. So now we can substitute what r is, and we are very happy again. So in this exercise now introduce to you the region of convergence. This is r. R is dependent on z, because a is fixed. A is the sequence, the geometric sequence power. So z depends on us. We are going to give different z's to compute. So only when this term is less than 1 is is the computation equals to this equation. Otherwise, it is not the correct answer. So we have now found out why this equation is the Z-transform of the sequence. So please take a minute to revise this if you're unsure. And in the next few slides, we'll show you the surface of this Z-transform. Thank you.